Right, hello, good evening, good day, good morning, wherever you are. Yeah, the stream started a bit late, but anyway, hello freaks. Yeah, I just got back. Well, I literally just got back from traveling. It wasn't really that far, but the traffic a bit. There was a bit of unexpected traffic. Not too much, but it delayed me just enough to be late to this stream. All right. Uh, okay, so for today, I have CJ. It's not here yet, so I actually don't know what we'll be going through today. Or am I actually streaming? Yes, I am. So, hmm. I need to just change the descriptions while we're away. So, okay, so while we're waiting, there we go. All right, so let's just check into YouTube real quick. Okay. All right, so this will be okay. I just got a message. Well, okay, so if you're a bot, then I won't respond. But if you can hear me, if you're an actual person, I am. Well, I'm happy. I'm glad you're offering this, but I'm not into doing this right now. So thank you anyway for the offer. Hmm. Ah. All right. So while we're waiting, okay. So I did send a message that I would be late to the student, our student today, CJ. Um, I think he's also not around because he hasn't responded to my message yet. But I'll refresh the page just in case there's something wrong with my page. All right, so while we're waiting, I hope everyone can hear me properly. Let me set up the rest of my. Let me just set up my tablet here for writing. And once we're ready, I don't think I've set it up yet. Okay, not yet. Hmm. All right. Okay, let's try that one more time. Hmm. Can't detect my tablet at the moment. Let's try that again. There we go. All right, while I'm bored, I'm gonna talk. While we're waiting, I'm just gonna talk here. There we go. Hold on. Let me set up the board real quick. Yep. All right. So for those who are wondering why we are streaming a bit late today, well, it's a holiday here today where I am. Again, for those who don't know where I am, I'm in Jakarta. That's in Indonesia, and today is a holiday. Okay. And Indonesia being a predominantly Muslim country, the holiday is about Muhammad rising up to heaven. For the Christians, it's very similar to how Jesus rose up to heaven after his resurrection. What's the date today? Today's the 8th of February. Okay. Where is my... There we go. Okay. Okay, let me just change my settings here so we can see my board. There. Okay. Well, I'm gonna message student CJ later. I'll still be waiting because I did tell him that I would be late, so I'll be waiting for about 30 minutes. Then I'll ask him what happened. If it's a reasonable, normally if it's a reasonable uh, excuse, I'll just use the word excuse here. Okay. If it's a reasonable excuse, I usually reschedule this class for no charge. But if it's like for, um, they just actually forgot, the student just actually forgot, or you know, any reason that wouldn't be excused in any other situation, normally I do not reschedule those lessons. Yep. Hmm. Somebody's watching me. Okay. All right. So while we're waiting, today's topic is supposed to be about waves, specifically the properties of waves that would be tackled in IB physics. Okay. Still waiting. Hmm. Okay, so might as well talk about this while waiting. Okay, so let me just open up something here just to be sure that I am accurate with what I'm teaching. What am I opening? The data booklet for IB Physics. Go back to desktop real quick. Where did I put that data booklet? All right, so while I'm checking out the data booklet, there we go. I'm checking out the data booklet here because I want to make sure that I'm teaching the right thing, because not everyone remembers everything. Okay. Right. Data booklet's not useful because there's only like two. Um, yeah, there are only two equations from topic of subtopic 4.1 and 4.2. That would be the ones that CJ was asking me about. Topic 1 is about oscillations in general, and then topic 2, 4.2 would be about traveling waves, basically how waves are produced and travel through space. Okay. Uh, Still waiting. I'm not gonna wait forever, just so we know. But I will ask him if he's okay at this point. Ah, okay, so let me open the textbook that I usually use, just real quick for reference. This one. There we go. All right. Reason I'm not sharing it is, of course, this information is copyrighted, even though the topic itself and um, the topic can be seen online for free. It is available to everybody for everybody, just basically free for everyone. But the one I'm looking for is copyrighted with all the descriptions, the diagrams, everything. And of course, I want to respect copyright whenever I can. I have sort of met the author of the book I'm using, sort of. Okay. The reason I say sort of is because I'm in the same Facebook group as the author of this book, and though, of course, he being the author of the book, he would be very active in that group, right? I'm pretty active in that group too. Sometimes I'm wrong. Yep. Yes. Yes, I get stuff wrong too. But most of the times I'm there to help. That's why I'm pretty active because a lot of people who ask are like they ask because it's not most I'm not saying that this is a bad thing. I think this is actually a good thing. Some teachers are actually teaching certain topics that they are not actually they're not trained to teach. For example, this is what I mean. Some of the physics teachers I see in that group are actually math teachers, for example, or chemistry teachers or biology teachers. That's not a bad thing. It's actually a good thing because it kind of helps expand the horizon of the teacher a bit, and at the same time, they can put their own unique perspective into the topic. Like for example, more mathematical technique, some mathematical techniques that will be more useful as compared to what's usually taught. Okay. All right. So I'm looking at the topic. I'm just making sure that this is all correct. Ah, okay. Everything here seems to be seems to be okay. This is the one thing. Wave fronts and race. I think that will be a bit confusing. We'll get to that later. And the principle of superposition. Okay. I think that's the most important bit. Reflection of pulses and polarization as well. That's 4.3 actually, I think. Let me double check. Yeah, wave characteristics. So polarization, wave fronts are 4.3 already. Uh, okay, so while we're waiting, let's wait a bit more. If CJ doesn't show up soon, like maybe another 10 minutes, in another 10 minutes, I'll just stream this real quick. And okay, but I gotta check if he's back online yet. He's not here yet. I'm gonna double check if he has joined yet or not. All right. Nope, not yet. He hasn't joined yet. Hmm. If anyone's watching the stream, can you comment? How do I sound? I'm just talking with my normal voice. I'm not really with my normal speak to myself voice. So this is my speak to myself voice. When I speak to somebody else though, whether it's face to face or online or whatever, I have a different there's a different level of excitement to my voice usually. But when I'm alone, when I'm streaming just by myself like this, I usually talk like this. It's more modulated. Uh, I don't know why, but I guess it's easier for me to answer a question when I hear it rather than think of something to say. Yeah, CJ isn't around still. All right, so this is what I'll do. I'll stick around for a while. Hmm. Hey, where's my calculator? It's gone. There. Hmm. All right, since it's not around yet, let me go back to the main board. Oh, I was never here on this board, was I? All right, let me go back to the main board then. Okay. All right. I'm not expecting my students to be here today, simply because it's a holiday. Okay. I've been here for 17 minutes, or 18, and still nothing. All right, so while we're waiting, I might as well do that. Let's go to the outro screen for a while. Again, if you're not doing this, please follow us here in these channels. Here's an update. The Freaky Physics for Twitch has been updated. The underscore has been taken out. So we're now just Freaky Physics, not Freaky underscore Physics. So apparently we can do that for Twitch, and I've removed the underscore. For Instagram, I think there's another Freaky Physics account out there that beat me to the name, so I really cannot change this to the no underscore bit. So only Instagram is the one with an underscore. And of course, for YouTube, they always attach these numbers. They don't really just leave you at Freaky Physics, for example. They always attach these numbers for some reason. Uh, so anyway, from on the different platforms, go ahead, please give us a like, subscribe, share, whatever. Okay. Uh, I'm actually working on a Patreon right now. I have a Patreon, but it's not active yet simply because I don't know how to work it yet. I'm still learning the intricacies of it. So, no Patreon yet, but I am working on it. But yeah, I'm doing this. As you can see, I'm actually using a green screen. This is what I look like without a green screen. Well, let's take that green screen out real quick. No. Let's go back to main. Okay, green screen. It's a bit dark. Ah, all right, let's put that back on. Okay, I've been here for 20 minutes. I guess I'm going to start talking about something still related to waves so we don't really waste our time here. Yeah. All right, so waves. So now that we've done oscillations last time with CJ, oscillations, just as a reminder, is the word oscillation. Let's go back here. Let's go to the board. Okay. Now I'm just gonna go. This is the blank board. I think I'll get out first because I want to show the old board from the last stream. Well, not the last one, but the one for CJ. The last one for CJ. Where's that? Okay. So let's start with this. Okay. So All right, so just as a recap from last time, where did I put my pen? Now that I'm actually want to say something, I have forgotten where I placed my pen. Oh, here it is. I think I put it behind me. Yep, pen's here. All right, so again, let's go back to this term oscillation. So oscillation again is any back and forth motion. Any back and forth motion is an oscillation. However, simple harmonic motion is mentioned here. Okay, so again, for simple harmonic motion, this is the primary condition, that the acceleration is directed in the opposite direction of the displacement and that they are proportional to each other. So directly opposite and directly proportional. Okay, so what does this mean? Another way you can think about this is there's a restoring force, or there is a force that attempts to restore. I think I misspelled attempt there. Yep. Oh, I didn't. Never mind. Attempts to restore the position of the particle, okay, to the equilibrium position. Now, of course, that being a force that attempts to restore stuff, that is basically called a restoring force. This restoring force is usually a single force that depends on the situation. Okay, so here's another way of thinking about it. All of these things are related because if you don't have a force, then you don't have an acceleration, and if you don't have a force, putting it back to the what's this, to the equilibrium position, you're never going to go back to equilibrium, right? All right, so again, these are the key conditions. We've looked at how graphs look like. Basically, this is what the acceleration, this is what the acceleration versus displacement graph looks like for a simple harmonic oscillator. Other oscillators would have different graphs. Okay, this is basically how um, a distance displacement or a time. Let me just write this here. So this is for distance displacement, or displacement distance rather. Let's read in the right order. So displacement distance or displacement time graph. They look very similar, but they will have different meanings. But I guess, like I said last time, it's easier to actually see how they differ once we actually uh, see them in action. Okay, all right. So for now, let me do a quick transition back to the main board. So that's the recap for waves that we did last week. No, last meeting. That was last Sunday, if I'm not mistaken. Last Sunday was the the 4th of February. Today's the 8th. Okay. All right. Let me just send a message. Okay, hold on. I'll just send a message. Okay, hold on. Okay, as you said. All right, so going back. So what does oscillations have to do with waves? I've described this before. I want to actually make a quick video on this later on, but uh, well, of course, the easiest way for you to think about this is if you have a particle. In fact, what I'll do is I'm going to not use the board. I'm going to use a simulation. Hold on, let me just go to the simulation first before I show you the board. Okay, give me a moment. All right, so in case you're wondering which simulation website am I using, I usually use the fet.colorado.edu website. It's got amazing simulations. All right. Okay, give me a few more moments. I want to do this real quick. All right, here we go. Simulation's ready. Let's see if it can be seen on the board. Right. So here, okay, here, this thing here is a string, and this I can manually change it like that. And you see that whenever I do that, the disturbance I cause travels. So this is what I meant earlier by when um I mean that a disturbance traveling through an object is a wave. Okay, there, like that. Whenever there's a disturbance on the string, there's a change in the position, a wave travels through it, like that. Now, you will notice here at the bottom, I have this damping very close to, but not exactly zero. That's on purpose for now, but I'm gonna put that to none now because this is what happens when you have no damping. The wave doesn't really diminish anymore, right? Oh, and here, you see something weird here? See something weird happening? What's happening? This is not something that you would normally see in any wave because a lot of people don't see this kind of behavior for a wave. So, okay, let me reset this and put the to zero. All right. So, I'm gonna change the settings real quick. So right now we have a fixed end. If I change this to a loose end like this, and I'm gonna change the settings further. Okay. So here I'm gonna change this to a fixed end, and what I'll do is I will send a pulse. Now a pulse is basically a wave that doesn't really repeat, like that. Okay. So what you can do here, what you can look at here is that uh, hope you can see my cursor. You cannot. It's okay. I'll change to this. Okay. So here, this is a fixed end. This is also a fixed end right here. Okay. Now I'm gonna pause this quickly and okay. Before I do so, okay. Oh, hi Jackie. I see you there. Jackie So Pro 1. Can you see it now? Jackie's watching on Twitch. What do you mean we? You have somebody still cannot see it? Ah, okay. How about now? Can you see this now? All right. Okay. Well, Jackie, thank you for coming to the stream. How many are watching on Twitch right now? I just want to check real quick. Nah, I'll just check after the stream. Anyway, so the idea here is let me reset the whole thing again. Okay, so I'm going to reset. I'm gonna put you on pulse. I'm gonna reduce the damping to 0 for now. Okay, now I'm going to change this. I'm gonna put the rulers up as well. So I'm gonna pick that right there. So I'm gonna put this 2 right there. So you can consider that 2 to be like the very beginning, the equilibrium position, right? So if I send the pulse out, and I'm gonna pause that right there. Right. I'm going to just put this ruler up here, and you can see that the amplitude is from 2 to 1, 2, 3, around 2.75, right? So if this is at 2.75, you start at 2, then the amplitude, that's just the height of the wave. That's the amplitude right there. Okay. Uh, so the amplitude here is 0.75 centimeters, and that's what it means right here. Okay. We will ignore this for now, the pulse width. It doesn't really mean anything for us. Okay. Now, what I want to go through here is the IB stuff, the IBDP stuff. Okay. Now you see that this wave, if I unpause this, I'm gonna step this so you can see where it moves. It's actually moving to the right. Okay. Now, as the wave moves to the right, keeps moving, you will see that the particles themselves don't really move forward or backward. They just move up and down. So let's take a look at this particle. It moves up or moves down, right? This particle moves up. Okay, we'll stop it right there. An interesting thing happens here though. Okay, you know that this end is fixed, right? So if you think about it, if I step the wave up one little bit, and I'm gonna keep doing that like that, just gonna keep doing that. Okay, you will see that the wave eventually kind of disappears, and then on the next step it reappears on the other side. It was up that dot, it was above the dotted line earlier, now it's below it, right? And if you look here, the amplitude of the wave is still 0.75 because you go from the 2 centimeter mark here. How low is that from there? So 0.5 is here, this is 0. This is around 0.2345. So this should be 0.2, 0.4, 0.6, 0.8. This should be around 0.8 or 0.75 in this case. Yeah. Okay. So the amplitude is still 0.75, but it's now in the other side. Why did it flip over? All right, I'm gonna do the same thing again. I'm gonna keep doing that, that, and remember that here, this is a fixed end. Okay. Now, as we do that, we keep playing. Oops, oops, it goes up, and then it goes back to the other side. Okay. Now, this happens because of the fact that they're fixed. These ends are fixed. So if they're fixed, okay, I'm going to step it over here. Okay, at this time, because it's fixed, think about it this way. The particle is going to try to go up. This one particle here is going to go up. Now, I'm going to switch over to the board. I'm going to take a quick screenshot of this thing, and I'm going to switch over to the board. Just up to here. Switch to the board. Right. Okay, so at this point, the wave, so the main thing here, let's go here. Okay, black should be okay. So, okay, okay, the wave transfers energy to this fixed end. Now, I want to say it transfers energy, but it doesn't really help us see what's happening. But so instead of saying that, I'm gonna say the wave exerts a force, exerts an upward force on the clamp. Okay, so this means, for those who are not familiar with this, so I'm just going to say by Newton's third law, okay, by Newton's third law, the the clamp exerts a downward force on the wave. Again, saying it like this is not exactly correct. I'll say the better way of saying it later. Okay, but the way to imagine it first, it's like this. By Newton's third law, the clamp exerts a downward force on wave, right? So we can mark that like this. So the force on the clamp is up, force on clamp. But that means the force on the wave or the particle, I'm just going to say the particle, the force on the particle is down. Okay, now because of that, what happens? As the wave progresses, this particle actually doesn't go up anymore. This particle starts going down. And that's what happens as we continue with the stepping. So if we go back here, if we continue with the stepping, you they still kind of go up, but they don't go as high up anymore, right? Because they're being forced down while they're moving up. So boom, and then there. The force eventually wins, causing the whole wave to move below the line. That's the reason why if you have a fixed end, a wave will flip over once it goes over to the fixed end. Okay, now what if you have a loose end like this? Okay, so let's play this first. Okay, on the fixed end here, you see it still flips over, but here on the loose end, it just, when it gets reflected back, nothing happens. It stays on the same side. It goes back, but it stays on the same side of the dotted line, either above it or below it. Okay, the reason behind this is the exact same idea, but the opposite effect as the previous one. Okay, so what's gonna happen here? Uh, I'll give you some think time. If you'd like to put it in chat, go ahead, put it in chat. But just some think time's enough. Now, if there are any teachers there watching the stream, of course, giving think time like this is a good idea for students because it kind of okay, because the idea is a student would normally still want to participate in the lesson, and giving this think time gives them time to generate their own ideas, right or wrong. It's still a good thing because it helps them get better with their critical thinking skills. Again, for the students, I'll give you a bit more thinking time. I'll give you one clue if you still are stuck. The clue here is it's still reliant on Newton's laws of motion. All right. So after this little bit, I'm going to end the stream because it's already 7 o'clock where I am. I'm gonna have to do some other things. But okay, let's go to the explanation. I'm gonna pause this first. Okay, so I'm gonna say it out loud first again, yeah? So I'll write it down later. So as the wave moves through here, because it's a free end, there is nothing stopping this end, right? There's nothing stopping this end from moving. So if you look at this carefully, yeah, the end moves along, right? And because the end can move, there is no force acting. There's no vertical force. There's a horizontal force of sorts acting horizontally. That's what reflects the wave. But vertically, there is no force acting on it. So because there is no force acting on it, it just acting on the wave particles just move as they do, even similar to like if the loose end wasn't there, if the similar to what if you had no end. Okay, so the loose end keeps going, it just gets pulled back by the wave itself. So because of that, since there's nothing making it go the other way, it's gonna stay on the same side. And hence, when it's reflected, it stays the same on the same side of the dotted line. Okay, so again, I'll play that real quick. Okay, and then I'll take a quick screenshot and just discuss that briefly. All right, so again, on the screenshot, let's take a look at this. So which one of Newton's laws is going to be useful here? It's not the third law anymore. It's now going to be the first law. So here, no force vertically, right? Vertical, to prevent the wave from moving, right? Okay, and then, so that's the first part. So that means the second part here is, since there's no force means Newton's first law. The, okay, law of inertia. So what happens? So the wave's inertia, wave particles inertia, allows it to stay on the same side, or lets it stay on the same side that it started on. Okay, lets them stay on the same side of the dotted line of equilibrium that they started in. Okay, okay, so that's the reason why if you have a loose end like this, when your wave is reflected, it stays on the same side. Now, for any SL students out there that may or may not be listening, okay, or who may be viewing the stream later, for any SL students out there, this is all you need to know. For HL students, this is the basis for thin films later on how thin films behave. So again, for SL students, this is all you need to know. For HL students, this is the basis for thin film interference. Okay. All right. It's already 7 o'clock. It's past that. At this point, anyone still on the stream? Jackie still there? I'm just wondering. Okay, let's go back to the main. Let's go back to the main board. All right. Well, if you're still there, thank you for joining. All right. Again, I'll just end it here. And again, don't forget to follow us on the following. I'm just so we're clear. I'm also working on a Patreon, but it's still not ready because I'm still studying how it works. Okay, so if once that's up, I'll let you guys know. Okay, so with that, we'll end the stream here. Thank you for joining, those who joined, and I'll see you again. Stay freaky, everyone. Bye bye now.